Let's look at the Laplace transform of a second-order differential equation with a step function. Why use Laplace transforms? They enable us to solve differential equations involving discontinuous functions. Here's the best known discontinuous function. For a is greater than 0, define the function u of t minus a to be 0 if 0 is less than or equal to t is less than a, and 1 if t is greater than or equal to a. Here's what the graph of u looks like. So it's 0 until we get to a, and then at a, it jumps to 1. This is a step function or a Heaviside function named after Oliver Heaviside. Ironically enough, he doesn't appear to be on the heavy side. Solve the initial value problem involving this Heaviside function. Y double prime plus 4y equals e to the negative 5t, u of t minus 2. Rather unfortunate name. At least he wasn't on the heavy side. Interesting. Let's look at the Laplace transform of a second-order differential equation with a step function. Why use Laplace transforms? They enable us to solve differential equations involving discontinuous functions. Here's one of the best-known discontinuous functions. For a is greater than 0, define the function u of t minus a to be 0 if 0 is less than or equal to t is less than a, and 1 if t is greater than or equal to a. Here's what the graph looks like. It's going to be 0 until you get to a, and then at a, it jumps to 1. This is a step function or a Heaviside function, named after Oliver Heaviside. Really interesting last name there. Here's an initial value problem involving the Heaviside function. Solve the initial value problem y double prime plus 4y equals e to the negative 5t, u of t minus 2, y of 0 equals 5, y prime of 0 equals 6. So here's what u of t minus 2 looks like. It's going to be 0 until we reach 2, and then at 2 it jumps to 1. But we don't have u of t minus 2, we have e to the negative 5t u of t minus 2. Here's what that looks like. It's 0 until you get to 2, and then at 2 it jumps to e to the negative 5t times 1, or in other words, just e to the negative 5t. So basically this function is like e to the negative 5t, but it starts at 2. We start by taking the Laplace transform of each side. And there are formulas that enable us to evaluate Laplace transforms. I'm not going to give you the definition in terms of integrals. We saw that in an earlier video. We have formulas for the Laplace transform of y. That's just capital Y of s. Laplace transform of y prime, y double prime. Mercifully, the Laplace transform of the sum is just the sum of the Laplace transforms. And the Laplace transform of a constant times x, a constant times f, is that constant times the Laplace transform of f. So you can pull constants to the outside. We have formulas for the Laplace transforms of 1, t to the n, square root of t, e to the at, t to the n, e to the at, sine kt, cosine kt, sinh kt, cosh kt, e to the at sine bt, e to the at cosine bt, etc. If you don't see what you need here, you can just go online. There are plenty of Laplace transforms tables online. They've got what you need. So again, going back to this initial value problem, let's start with the left side. Left side is L of y double prime plus 4y. In other words, it's the Laplace transform of y double prime plus 4 times the Laplace transform of y. We're breaking up the sum and we're pulling out constants. We've seen before that this is the formula for L of y double prime, and L of y is just going to be capital Y of s. Now let's plug in 5 for y of 0, and let's plug in 6 for y prime of 0, and we end up with this line. Simplify a little bit, and we get s squared y of s minus 5s minus 6 plus 4y of s. Okay, so let's look at the right side. That's the Laplace transform of e to the negative 5t u of t minus 2. We're going to use this handy-dandy formula. Laplace transform of u of t minus a, f of t minus a is e to the negative as times the Laplace transform of f of t. Here, since we're dealing with u of t minus 2, we can tell that a is going to be 2. So just plug a equals 2 into the above formula, and this is what we get. So now compare these two formulas. So here we have, let's see, so we compare these two formulas, right? This one and this one. So both of them have the u of t minus 2. This particular formula has e to the negative 5t. So we can see that if we're going to apply this formula, all we have to do is regard f of t minus 2 to be e to the negative 5t. So f of t minus 2 is e to the negative 5t. Ooh, boy, it would be really helpful if we knew what f of t was. We can do that. Just replace t with t plus 2. Then we'd have f of t plus 2 minus 2 is e to the negative 5t plus 2. I did that because t plus 2 minus 2 is just t. So this equation simplifies to f of t equals e to the negative 5t minus 10. You can break that up as e to the negative 10 times e to the negative 5t. Okay, so in other words, we have the Laplace transform of u of t minus 2, f of t minus 2 is e to the negative 2s times the Laplace transform of f of t. That's what we had above. This, in other words, is going to be e to the negative 2s times the Laplace transform of e to the negative 10, e to the negative 5t, because that's what f of t is. We just saw that a moment ago. Let's plug that in for f of t. And that can be rewritten as e to the negative 2s, e to the negative 10 times the Laplace transform of e to the negative 5t, because e to the negative 10 is just a constant. Okay, so this is what we get for the right side. Boy, wouldn't it be cool if we could evaluate the natural log, the Laplace transform e to the negative 5t? We can. We're going to use this formula. So plug in negative 5 for a, and we end up with the right side as e to the negative 2s, e to the negative 10, and the Laplace transform of e to the negative 5t is just going to be 1 over s plus 5. So in other words, we have e to the negative 10, e to the negative 2s over s plus 5. Okay, putting the pieces together, the left side equals the right side. Boy, did that take forever. Ultimately, we want to get capital Y of s all by itself. So let's pull those factors together. We have s squared plus 4 times y of s minus 5x minus 6 equals e to the negative 10, e to the negative 2s over s plus 5. Okay, we can pull the negative 5 minus 6 to the other side, and we end up with this over here. Divide both sides by s squared plus 4, and we get y of s equals e to the negative 10, e to the negative 2s over s plus 5, s squared plus 4, plus 5s plus 6 over s squared plus 4. And we can break this up using partial fractions. Then we can use the inverse Laplace transform. Recall partial fractions from Calculus 2. So basically what I'm going to do is we're just going to cast this aside. We'll pull this out for a moment and just focus on 1 over s plus 5 s squared plus 4. From what we learned in Calculus 2, 1 over s plus 5 s squared plus 4 can be written as a over s plus 5 plus bs plus c over s squared plus 4. It's not just a constant over s squared plus 4 because s squared plus 4 is an irreducible quadratic. So you can't have just b over s squared plus 4. It's got to be linear. It's got to be bs plus c over s squared plus 4. Let's multiply both sides by this denominator, and we end up with 1 equals a times s squared plus 4 plus bs plus c times s plus 5. Plug in s equals negative 5. Why am I doing that? Okay, if we're going to solve for a, b, and c, we're just going to recognize that this is going to be true. This formula is going to be true for all values of s. So let's plug in strategic values of s. If you plug in s equals negative 5, this term goes to 0. That's strategic. So we get 1 equals a times negative 5 squared plus 4 plus b times negative 5 plus c times 0. In other words, we end up with 1 equals 29a, or a equals 1/29. Awesome. So let's plug in 1/29 for a. Now let's find what b and c are. So here, again, we can plug in any old value of s. That should be fine. There's really no more strategic values of s. So plug in s equals 0, for example, and you'd end up with 1 equals 1/29 times 0 squared plus 4 plus b times 0 plus c times 0 plus 5. In other words, 1 equals 4/29 plus 5c. 1 minus 4/29 is 5c. 25/29, in other words, is 5c. So c equals 5 over 29. Awesome. Let's plug that in for c. Lastly, let's find b. Plug in any value of s, like let's say s equals 1. And we get 1 equals 1/29 times 1 squared plus 4 plus b times 1 plus 5/29 times 1 plus 5. Simplifies to 1 equals 5/29 plus b plus 5/29 times 6. That's 5/29 plus 6b plus 30 over 29. We can combine these two guys, the 5 over 29 and the 30 over 29, and get 1 equals 6b plus 35 over 29. Move the 35 over 29 to the other side. We end up with this. Simplify, we get negative 6 over 29 equals 6b, so that b equals negative 1 over 29. Okay, we found the a, b, and c. So this expression can be rewritten this way if we break it up using partial fractions. Okay, plug in the a, b, and c, we get this. Awesome. So recall that capital Y of s looked like this. So this 1 over s squared plus 4 can be replaced with this, and that's what we get. So we have capital Y of s equals e to the negative 10, e to the negative 2s times this hairy expression that we just found by plugging a, b, and c, plus 5s plus 6 over s squared plus 4. Okay, so again, capital Y of s looks like this. So now let's just take the inverse Laplace transform of both sides. Inverse Laplace transform of capital Y of s is pretty easy. That's just going to be y, so we're great there. And then we have these hairy inverse Laplace transforms on the right side. Recall we can break up sums, pull out constants, and when we do so, we end up with 1/29 e to the negative 10 times the inverse Laplace transform of this, plus negative 1/29 e to the negative 10 times the inverse Laplace transform of this, plus 5/29 e to the negative 10 times the inverse Laplace transform of this, plus 5 times the inverse Laplace transform of this, plus 6 times the inverse Laplace transform of this. We have our work cut out for us. We need to find some inverse Laplace transforms. We want the right side of the equation to be the Laplace transform of stuff. So we can take the inverse Laplace transform of each side, and then the right side would just be stuff. But we don't have anything on the sheet that enables us to represent, say, e to the negative 2s over s plus 5 as a Laplace transform of stuff. Yeah, this first one. Well, we don't know what the inverse Laplace transform of e to the negative 2s over s plus 5 is. We haven't seen that. It's not on any of the sheets. However, when we have e to the negative as times something we already recognize as a Laplace transform, we can use this handy-dandy formula. The Laplace transform of u of t minus a, f of t minus a, is e to the negative as times the Laplace transform of f of t. In this case, we can see that since we're dealing with, in this case, we can see that we're dealing with a equals 2 because we have e to the negative as here, and this is e to the negative 2s here. So a equals 2. Plug a equals 2 in, we end up with this. Now let's see. When we compare these two, e to the negative 2s, Laplace transform of f of t, gosh, when we compare these two formulas, this looks like the Laplace transform of f of t is 1 over s plus 5. So if we're going to use this formula, it would be great as long as the Laplace transform of f of t is 1 over s plus 5. Oh, that's great, because based on what we've seen before, that means f of t is e to the negative 5t. Awesome. Okay, so we have f of t equals e to the negative 5t. Plug that into the formula above. In other words, plug it into this formula. And here's what we end up with. Laplace transform of u of t minus 2, e to the negative 5, t minus 2, because we're not evaluating just f of t, we're evaluating f of t minus 2, equals e to the negative 2s times the Laplace transform of e to the negative 5t. That is, in other words, e to the negative 2s over s plus 5. And now, we're just going to take the inverse Laplace transform of each side. This is awesome, because that's the Laplace transform of stuff. So the inverse Laplace transform of that is just going to be stuff, okay? So now we multiply out the exponent, and we have u of t minus 2, e to the negative 5t plus 10 equals the inverse Laplace transform of e to the negative 2s over s plus 5. Okay, that's awesome. We found the inverse Laplace transform of that factor. Let's keep moving. Now we want to find the inverse Laplace transform of e to the negative 2s, s over s squared plus 4. Again, we're going to use this helpful formula. We're going to plug in a equals 2, because we can see that a equals 2 in this formula. we end up with e to the negative 2s times the Laplace transform of f of t. Okay, so we have e to the negative 2s times the Laplace transform of f of t. So that stuff's got to be the Laplace transform of f of t. Okay, so now we need to solve the Laplace transform of f of t equals s over s squared plus 4. Well, we actually have a formula for that. That means f of t equals cosine 2t. So the Laplace transform of u of t minus 2, cosine of 2 times t minus 2. All we're doing is plugging in cosine 2t for f. This is what the left side is going to be, and the right side is going to be e to the negative 2s times the Laplace transform of cosine 2t. In other words, the Laplace transform of u of t minus 2 cosine of 2t minus 4 is e to the negative 2s, and again, this is going to be the cosine of 2t, Laplace transform of that. Take the inverse Laplace transform of each side, and we end up with u of t minus 2 cosine 2t minus 4 equals the inverse Laplace transform of this stuff. That's awesome. That's another inverse Laplace transform we needed. Okay, so we had e to the negative 2s over e to the negative 2s s over s squared plus 4. Now we have just plain e to the negative 2s over s squared plus 4. Use the formula we've seen before. Plug in a equals 2. We end up with that. Okay, so again, we can see that we have e to the negative 2s times the Laplace transform of f of t, and the Laplace transform of f of t is going to be 1 over s squared plus 4. Notice that means that f of t is going to involve sine 2t, based on what we've seen on the Laplace transform sheet. The Laplace transform of sine 2t is not 1 over s squared plus 4, it's 2 over s squared plus 4. So that means the Laplace transform of a half sine 2t is going to be 1 over s squared plus 4. So plugging that into the formula above, in other words, plugging in what we need for f of t, so we end up with u of t minus 2 times sine of 2t minus 2 all over 2 equals e to the negative 2s Laplace transform of 1/2 sine 2t. Because again, I may not be making this clear, but this is what we want for f of t. So this is just going to be, that's just going to be f of t minus 2 from up here. Okay, so when we simplify that, we end up with the Laplace transform of u of t minus 2 sine of 2t minus 4 all over 2 equals e to the negative 2s s squared plus 4. Take the Laplace transform of each side, and this is what we end up with. The inverse Laplace transform of this stuff, that's another inverse Laplace transform we needed to know, equals this. Awesome. Okay, mercifully, these last couple ones are pretty easy. The inverse Laplace transform of s over s squared plus 4, that turns out to be cosine 2t. Inverse Laplace transform of 1 over s squared plus 4, well, the Laplace transform of sine 2t is 2 over s squared plus 4, so the Laplace transform of 1/2 sine 2t is 1 over s squared plus 4. That means the inverse Laplace transform of 1 over s squared plus 4 is 1/2 sine 2t, just from taking the inverse Laplace transform of both sides. Oh my goodness, we are near the finish line. So this is the slide we saw earlier. We have the inverse Laplace transform of y of s equals blah, 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 times this inverse Laplace transform, etc. Now we're going to replace all these inverse Laplace transforms. Okay, we've seen what this left side is. That's just plain y. So we have y equals 1/29 e to the negative 10 times the inverse Laplace transform. That's what we wanted to find. Plus negative 1/29 e to the negative 10 times the other Laplace transform. Plus 5/29 e to the negative 10 times this Laplace transform. Well, inverse Laplace transform, really. Plus 5 cosine 2t plus 3 sine 2t. Oh my goodness, we made it through. I know it was brutal, but I really wanted to show you this example because otherwise, if you're trying to solve these without seeing a hairy example like this, it's so easy to get lost.